Welcome to This Explainer. Today, we're shining a massive spotlight on the internet's unsung hero, the transport layer. Seriously, this is the invisible, tireless engine running behind the scenes just to keep our digital lives organized. Whether you're streaming a video, firing off an email, or just browsing the web, the transport layer is that absolutely critical piece of architecture making sure the right data gets to the exact right place on your device. Without it, well, the internet as we know it would literally be a chaotic, tangled mess. But as we're going to see, the very rules that make it so incredibly helpful also make it highly dangerous in the wrong hands. I mean, really think about that for a second. We build these massive million-dollar network infrastructures, complete with state-of-the-art firewalls and dedicated security teams. And yet a clever attacker sitting in a basement halfway across the world can send just a few meticulously crafted bytes of data and bring a giant corporate server completely to its knees. How is that even mathematically possible? Well, the answer is actually hidden deep within the rules of the transport layer itself.
Okay, let's dive into this. First, we'll meet the transport layer. Then, we'll look at TCP versus UDP, explore the hacker's playground, see how they weaponize TCP and UDP, and finally, how we defend the transport layer. Starting off with Section 1, meet the transport layer, the traffic cops of the internet.
Now, the textbook definition tells us that the transport layer provides logical communication between application processes running on different hosts. But, what does that actually mean in plain English? Think of it this way. The layer right below this, the network layer, is really just responsible for moving data between computers. It gets the data to your laptop, which is great. But your laptop is probably running a dozen different things at once, right? Spotify, a web browser, your email client. The transport layer is responsible for process-to-process delivery. It uses these things called ports and sockets to ensure your email data goes to your email app and your music data goes to your music app.
To really grasp this, let's look at a classic real-world analogy. Imagine two houses, one on the East Coast, one on the West Coast, and each is filled with a dozen kids who write letters to each other. The houses, those are the host computers. The kids are the application processes running on those computers. And the letters? Well, those are the data messages. Now, in each house, there's one kid, let's call them Ann and Bill, who actually collects the mail from their siblings, hands it to the postal worker, and then distributes the incoming mail back to the right siblings. Ann and Bill are the transport layer protocol. They're performing what we call multiplexing and demultiplexing. And this brilliantly illustrates the whole concept. Just like Ann sorting the incoming mail and handing it to the correct kid, the transport layer examines the incoming data packets, checks out their destination port number, and seamlessly routes them right to the correct application on your screen. It handles all the messy, complicated details so your apps can just focus on being apps.
Moving on to Section 2, TCP versus UDP, the two main flavors of data transport.
So it's basically a showdown. On one side, we've got TCP, which is the reliable, highly organized workhorse of the internet. It absolutely guarantees your data will arrive exactly as it was sent. On the other side, we have UDP, which is the fast, rule-breaking rebel. It really doesn't care if data gets lost along the way. It just wants to go as fast as possible. Let's break down exactly what makes them so different.
Let's start with TCP, the Transmission Control Protocol. This is kind of like sending a certified letter with a return receipt. Before TCP sends a single drop of data, it insists on a polite three-way handshake with the receiving computer just to establish a connection. It attaches a hefty 20-byte header to every single packet, meticulously labeling them with sequence numbers. If a packet gets lost, TCP notices the missing acknowledgement and resends it. It even has built-in congestion control, meaning it'll actually slow itself down if it senses the network is getting jammed up. It is incredibly polite and entirely focused on pure reliability.
And then there's UDP, the User Datagram Protocol. UDP does not handshake. It doesn't check to see if the other computer is even ready. It just starts blasting data at maximum speed. It has a tiny 8-byte header, so it's super lightweight. And because it has zero congestion control, it never, ever hits the brakes. You might be wondering, why would we ever want an unreliable protocol? Well, because for things like live video streaming, voice calls, or quick DNS lookups, speed is way more important than perfection. If you drop a single frame of a live video, you don't want the network to pause and go fetch it, you just want the next frame right now.
All right, Section 3, the hacker's playground, when the rules are used against us.
Seriously, consider this for a moment. TCP's politeness, its handshakes, its guarantees, UDP's raw, unthrottled speed, and total lack of verification. What actually happens when a malicious actor steps into the network and decides to use these exact engineering marvels as Trojan horses?
So, the crucial point here is that the transport layer fundamentally relies on trust. It trusts that when a computer asks for a handshake, it actually wants to communicate. It trusts that when a packet says it contains a specific type of data, it's telling the truth. Hackers don't necessarily break the rules, they weaponize them. They exploit that built-in trust to overwhelm systems or sneak malicious code right under the radar.
Which brings us to Section 4, Weaponizing TCP and UDP. Let's dissect some actual transport layer exploits.
Remember that super polite three-way TCP handshake? Well, here's how it becomes a deadly weapon known as a SYNFLA, denial of service attack. Step 1. The attacker floods the target server with thousands of synchronization requests, or SYN segments. Step 2. The server, being polite, allocates memory and resources for every single one, sending a reply and waiting for that final handshake confirmation. Step 3. The attacker simply never replies. The server is left holding open thousands of these half-open connections until it quite literally runs out of memory, crashes, and legitimate users are completely denied service. The attacker used TCP's own politeness to kill the server. Wild, right? Now, to understand how UDP gets attacked, we have to talk about a buffer overflow. This is when an attacker sends unexpected input that technically meets the networking protocol's specifications, so it gets let through the front door, but it actually contains massive amounts of data that the application's code was never designed to hold or process.
Now, what's really interesting about this exploit is how perfectly a buffer overflow pairs with UDP's connectionless nature. Take TFTP, for instance, a simple file transfer protocol running on UDP port 69. A normal request just asks for a simple file name, but hackers will target that exact field, injecting a massive payload of malicious code straight into it. And because UDP just blasts data without checking states, the server blindly tries to process this giant fake file name, overflows its memory buffer, crashes, and effectively allows the attacker to compromise the entire system.
Finally, Section 5, Defending the Transport Layer, securing the very foundation of the Internet.
Remember that devastating TCP SYN flood attack we just looked at? The defense against it is actually a brilliant mechanism called SYN cookies. Instead of the server immediately allocating precious memory for every single incoming handshake request, the server mathematically hashes the connection details into a cookie and sends it back to the client, allocating zero memory. It's only if the client returns that exact valid cookie that the server actually opens the connection. This totally neutralizes the SYN flood because those fake requests can no longer drain the server's resources. But what about the fact that basic TCP and UDP send all their data completely unencrypted, just open for anyone on the network to read? Enter TLS, or Transport Layer Security. You can basically think of TLS as a secure armored wrapper that sits right on top of TCP. Before the data ever hits the network, TLS encrypts it, ensures its integrity, and authenticates the endpoints. It means that even if a hacker intercepts your packets, all they're going to see is mathematical gibberish instead of your clear text password.
Which brings us to perhaps our best defense, ethical hackers. As detailed in resources like Georgia Weidman's penetration testing, ethical hackers actively probe corporate networks, hunting for these exact transport layer vulnerabilities like missing TLS or unpatched UDP services. They do this so they can help clients fix the holes long before the malicious attackers ever find them. It is an ongoing, high-stakes game of cat and mouse.
Which leaves us with this final thought. The transport layer is an absolute marvel of engineering, perfectly balancing the reliable delivery of TCP with the blinding speed of UDP. But as we've learned, every single feature is a potential weapon. So I challenge you to think about the networks you rely on every day. Are they truly secure, fortified with modern defenses, or are they just sitting there, silently waiting for the arrival of exactly the wrong packet? Keep learning, stay curious, and I'll catch you on the next explainer.